All right, so we'll start for the second part of the day. Now we start the blocks that we were telling you about. One of the blocks is about cobordism and applications. So Arun will start with the lectures, and we hope that you enjoy it. So please, Arun, anytime.
Yeah, so thanks so much for having me. Thanks to all of you for being here. I hope you enjoy these talks. So what's going to happen is Miguel Montero and I are going to give several talks on Boardism and its applications in various aspects of physics. So Miguel is feeling sick today, so I think he's watching via Zoom. So the order that we had planned, it might change up slightly, but I'll tell you what the plan is, and then we'll cover this roughly the same stuff, but it might be shuffled. So today is going to be this. So it's sort of I'm going to focus on the mathematical aspects thereof. And there's going to be applications. That's matter. So this is, if you've heard about SPT phases and the like, I'll tell you where that, the story of that, and then how Boardism enters the picture. The next talk is going to be, applications on field theory. This is really the anomaly. Now, if you ask 4 different physicists what an anomaly is, you'll get 5 different answers. So we're focusing on one particular perspective, which is anomalies as invertible field theories, from which Boardism enters the picture. And the 4th thing would be something like applications to string theory. Which is, for example, the cobordism conjecture of McNamara and Bappa. So I think out of all these applications, I think this is the one that is most interesting for people in this room. But hopefully these are also, hopefully these will also be interesting. And then there will be a talk on computations. So the really nice thing about Boardism, it's not just that it's useful, but it's also that we can compute it, especially in the range relative physicists. So we'll talk about some ways of doing that. So which talks will be given by, which subset of me and Miguel? Hopefully always a non-empty subset. We'll, we're gonna have to figure that out a little bit later. But so I guess, yeah, this is the plan. Today's a math talk. These are more physicsy talks, and then this one is a math talk with aimed at a physics audience. So for context, I am a mathematician, and though I'm a mathematical physicist, I don't really know a lot of physics. It's it's an interesting story how I got mixed up in this stuff. But the point is, today I'm going to give a math talk similar to something that I've given for other mathematicians. So if at any point, I made my best guess as to the right things to say for the audience, but if at any point anyone has any questions or any comments or any complaints with something I said about physics, please let me know. The goal is for you all to come away with an understanding. And so if something isn't making sense, or if I'm speaking too fast or unclearly, with the math, please let me know. I'm happy to. More questions is better. Let's see. So, and I mentioned this briefly during the beginning. Well, I guess I should tell you the outline of this talk. So, I'll talk about what Boardism is, not just some manifolds are boundaries of other manifolds, but more precisely how we think about all the different kinds of Boardism. There's oriented Boardism, there's spin Boardism, there's Boardism where you care about the symmetries of a 2 group, all of these fit under one general platform.
Just for the recording,
yes.
So that writing is marginal. If you can make it.
This one?
Yes. So
is it too small?
It is marginal, so always bigger than this.
Bigger,
so
okay.
Like this or bigger.
Okay, I can do that. Thank you. Great. So this could be like when I go get my glasses checked. It's like, can you see this letter? How about these letters? Right. So once we have that, then there's going to be a better name for this would be the Pentronian-Thom construction. So how do we actually compute Boardism proofs? is you find a space such that Bordism groups of a certain kind are the same thing as homotopic groups of that space. And the algebraic topologists have been working on these kinds of homotopic theory problems for honestly 70 years. They've been ever so patiently sharpening their knives. And now we have some physics applications for them to dig into. And so the tools that they have are really, really good. So this is the crucial result that allows us to get from this geometric question, Bordism groups, to the homotopical question, which is how these things are actually calculated. Then I'll talk a little bit about, well, physics. So this is still a mathematical result. So invertible field theories are mathematical objects. So you've probably heard that mathematicians formalize topological field theories in this completely transparent and very understandable formalism of a symmetric modal functor on some like higher category. So in my experience, physicists are always a little bit like, why introduce all of this stuff? But in the invertible case, we're going to end up getting back to Bordism groups. And so it turns out by result of Tweed-Hopkins-Telemon and Tweed-Hopkins, Bordism groups classify essentially unitary invertible field theories, which is the engine that powers these two applications. So I wanted to mention this because it's a story today, because it's a story that can be told completely in math, and hopefully it'll I guess make for a deeper understanding between or as to how these things appear here. So, I mean, it's also, in my opinion, just cool mathematics. So that's going to be the third part of the talk. So before I go on, let me pause. Are there any questions yet?
Abortionism of cobordism.
Ah, great, thank you. Okay, this is something that I should have mentioned earlier. Okay, there's a reason for this. So initially, when this stuff was first studied by, I guess, Steenrod and maybe Renee Tom, the word was cobordism, for, meaning sort of they jointly bound. So jointly, and then board as in boundary, hopefully not as in the sense of it's after lunch and I'm falling asleep in the seminar room. So cobordism, jointly bound. So then, I think it was Atiyah who discovered that cobordism is a generalized homology. And so there is therefore a corresponding generalized cohomology theory. And so he thought about it and said, it doesn't make sense to call the homology theory cobordism and the cohomology theory bordism. So if you follow Atiyah, there's two separate things, bordism, which is the homology theory, and cobordism, which is the cohomology theory. Now, it turns out that cobordism, the cohomology theory, is not as useful, especially in like these applications, as bordism. So when people say cobordism, you say cobordism, I say bordism, let's call the whole thing off, et cetera, et cetera. If you're not sure about this, just they're the same. Don't worry about the details about what I just said, because they won't come in practice. Yeah, thank you for asking. I meant to say this at some point, but it's better that I said it soon. Cool. Who has more questions? Okay. So, I do algebraic topology. And so the way that this tends to look in practice, there's the clock, is, let's start over here. So now the camera's on this side. Wait, what? Now the camera's, yeah. So, algebraic topology is this procedure that takes geometric or topological things and turns them into algebraic things. And so sometimes that might mean groups. It might mean algebras. It might mean vector spaces. It could even mean categories. So this is sort of the general idea of algebraic topology. And bordism fits into this perspective. So, you can think of this as like cohomology or even differential forms, where you take a manifold and you get out of it an algebra of differential forms, or the Durand cohomology coming from it. And so bordism is yet another example of this. So in bordism, is one of these. built from the question of which manifolds are boundaries. So, okay, here's my manifold, here's M, and here's a boundary. Let's just take the open cylinder. So every manifold bounds and we're done. Maybe not so exciting. So let's fix this by asking to bound a compact manifold. And then this is ruled out and the question is now interesting.
So, Arun, for the rule of the line, you need to be on this side.
Oh,
to be able to
like
see
really on
the
the
right.
side.
Yeah, perfect. Now,
Okay.
now you're perfect.
Cool. Yeah, thanks. This is good to know.
Sorry.
No, it's fine. Look, if we're doing like geometry, I should be all about lines. So, okay, so now we've ruled out this like silly example. So it turns out that not every manifold is a boundary. So sort of the first answer to this question so for example, RP2 is not. So I'm not going to tell you exactly how to prove this right now, but you can coax this out of a version of Stokes' theorem. So Stokes' theorem is about integrating differential forms. You want the version of Stokes' theorem that applies to mod 2 cohomology classes. So in some sense, one way which I learned to think about this stuff is a lot of the things that happen in algebraic topology start simple and then get more and more refined. So maybe you start out with like just these vector spaces of differential forms, and then you're promoted into something homotopy invariant, the Durand cohomology, and then you say, oh, this has a ring structure. And so it's just sort of like more and more elaborate. And then for Bordism, we had a yes or no question. And we're going to turn it a little more interesting. We're going to turn it into abelian groups, sometimes into rings, and eventually we're going to get Bordism categories, which will give us invertible field theories. But, so we started small, just does it bound, does it not? But we can then turn it into an equivalence relation.
Quick question.
Yes.
Are there examples of orientable manifolds of low dimension which are not the boundary?
How's CP2? Is that one? Do you like that one?
Okay.
Yeah, that is the smallest dimensional non-trivial example.
That's already like 4-dimensional.
Yeah.
Okay.
Yeah. So in dimensions 1, 2, and 3, there's nothing. Yeah, great question. More questions. Okay, so we get an equivalence relation. Two manifolds, so they're always going to be closed and compact. And we're going to say they're the same dimension. We call them bordant. And again, if you grew up calling this cobordant, I mean the same thing as you, and I'm happy if you use either word. But in the interest of writing 2 fewer letters, I will use bordant. So 2 manifolds are bordant. If there is a compact manifold X, and diffeomorphism of the boundary of X to M disjoint union M. So this is an equivalence relation. So I'll walk through the 3 things. So for reflexivity, M is bordant to M by the cylinder. M cross the inverse. It's symmetric. If I have a bordism from M to N, I can turn that around to a bordism from N to M. And it's transitive because bordisms group. So here's a bordism from M to N. And then here's a bordism from N to P. well, what can I do? I can just smush them together. And I've got an abortism from M to P. So the set of equivalence classes which is traditionally denoted omega n for the dimension. So I should say 2n manifolds. So it's denoted omega n. Sometimes I'm going to use O up here because I'm going to consider other variants later. Historically, this was denoted like math frac n, which I don't know how to write, but you know, actually, I have a solution. Yeah, so you'll see this in Renee Tom's original paper, for example, or Dold's paper, etc. So this is an abelian group. Under disjoint union. And in fact, if you consider this for all dimensions at once, this is a graded ring. Be a direct product. So this is, you know, there's some stuff to check. These operations are defined on manifolds, not on Bordism classes. So you have to check, okay, if M is boarded to M prime and N is boarded to N prime, is M disjoint union N boarded to N prime disjoint union N prime? You know, you can do this. I'm not like, I don't think this is the detail to worry about. But hey, look, we got a graded ring out of topology. So this and some variants, which I'm about to tell you, were some classical questions in algebraic topology studied in the 50s. Yes.
Sorry. N here is the dimension of X? Or
N is the dimension of M and N.
of N?
Yeah. Great.
Your manifolds are smooth
another
always.
So you can do this with more general things, but as far as I'm concerned, yes, they're always smooth. Yeah, thanks for clarifying.
In the beginning, you had said that, okay, Bordisms are called so because they are a homology theory rather than cohomology theory.
Yeah.
But usually it's in the cohomology theory where you have a ring structure, graded ring structure, right? So is
Yeah.
there like a nice answer, like why this is?
Why does that happen? Oh, that's a great question. So this is okay. So later when we turn this into a generalized homology theory, this is going to be the Bordism groups of a point. Now, if you took ordinary homology of a point, you get Z, which is notably also a ring. So, okay, I have to think this through. Is that? Yeah, I think that works. That's what's going on here. Is that if you took cobordism groups of a space, which is something slightly different, then you would get ring structures as well. But this is sort of separate from that, if that makes sense.
I think for a point, cohomology or homology is the same.
Right. Yeah. And so for the point, the sort of the cobordism groups and the bordism groups would be the same. Possibly, you know, you have to deal with the indexing, but in both cases you'll get the same ring. Yeah, great question. Did that answer? Okay, great. Who has more questions? Okay. Yeah. So this thing was, you know, these things were studied pretty intensely in like, you know, the 50s through the 70s, this and some of its variants that I'll tell you about. And so it's, like I said, you know, people turned this into a homotopy theory question and then attacked it that way. But let's see. Yeah, so this was solved by Tom, who's you know, with his work, this subject, you know, took several bounds forward. And then there was later work by Konchagin, Lashoff, Wall, Anderson, Brown, Peterson. Gilkey, Quillen, plenty of other people. So this story all takes place from like the 50s, maybe the 70s. And more recently, we have this story in physics. So various objects of interest in physics are Bordism invariants. You have some quantity that is on a manifold, And a priori, you want to know some fact about it. And maybe you can prove it with your bare hands. But alternatively, you want to check it on everything. And so you say, okay, I'd like to check it on every manifold at once. That's way too much. But maybe it only depends on the class of the manifold in this Bordism group. And then you can just check on a generating set. So there's lots of different there's lots of different things in physics. For example, anomalies that boil down to this kind of thing. And we'll see that a lot later in future lectures that Miguel and I do. But one thing which is I think worth mentioning, you have to modify the notion of Bordism to account for the fields. So for example, you might say, oh look, I have a manifold and I have a spin structure and I have some vector bundles associated to the spin structure, like the spinor bundle. And my Bordism question, well, it doesn't factor through this because it needs to know the spin structure. And so then you have to take a different kind of Bordism. So that's what I'm going to talk about next, is how to set up a general notion of Bordism. So when I talk about okay. So I think that the best thing to say about that is that there's lots of different variants. And the reason that you should care about that is you want to match what notion of Bordism you're doing to what the data in your physics question is. And if you're doing a math question, well, the same applies. But let's see. So variants of Bordism.
You said that this was solved by Tom and the other people from 50s to 80s. So what did they characterize this ring?
So Tom he figured out what this ring was and found many generators. I think found the remaining generators. And then there's a bunch of variants that I'm about to tell you about. And so a lot of these authors considered some of the more important variants.
One question, do we need to assume some kind of orientability for our manifold?
Orientability?
Yeah.
Not yet.
Oh.
So that's one of the variants, is what if you insist that everything has an orientation and this is compatible with that?
Okay, but for example, I will assume that as we are defining a group, the inverse would be like the same.
Oh yeah. Oh shoot, that's important. Yeah. So the inverse, I said this is an abelian group, and you take the inverse. So M is its own inverse. You take this cylinder and sort of move it around.
Okay.
And then you get a Bordism from M plus M to 0.
Okay.
And now I think related to what you're asking is those two copies will be oppositely oriented.
Yeah.
So when you do this in the oriented Bordism group, M is not its own inverse, but M with the opposite orientation.
Okay, but in like the basic definition of Bordism group doesn't need to specify the orientability.
Yes.
Okay.
Yeah, great. But then various refined notions do. Yeah, that's a really great question. I'm glad you asked. Are there more questions? Okay, so I'm going to talk about variance. So the way I said it back there made it sound like this was first considered by the physicists, or the people who talked to the physicists, but that is not true. This idea was considered by Lashoff almost as soon as Bordism was originally done by people like Tom. And so this is a way to sort of encode all of the topological data of the fields in some sort of theory into some mathematical object, and then take Bordism groups like that. So, so there is a space G, which is the classifying space for principal G bundles. So if this is something that you've seen before, okay. If not, this is one of the things about algebraic topology, is this space typically for like nice Lie groups like UN or like even U1 or whatever, this space is like horribly infinite dimensional. But the tools that we have with algebraic topology allow us to not worry about that and just still compute. The point is this space exists. And the space of maps to BG is homotopy equivalent to the space of principal G bundles on a given space. So it sort of solves this this moduli problem. But again, it's this weird, like, this is true up to homotopy and this is true up to isomorphism. So, so let's consider the topological group O, which I'm going to define to be the increasing union of your orthogonal groups ON. So where is this union taking place, you might ask? And that's when I say this is secretly a colimit. But you can really think of this as O1 sits inside O2 via, A001 block matrix, and that sits inside O3 and so on. And if you just keep doing this and you don't stop, you get this. And this is a topological group. So it turns out that, so there's a correspondence between vector bundles of rank n and principal ON bundles. So the idea is, I want to specify transition functions for a vector bundle. And so those are valued in, so I can think of this as I pick a basis of, I trivialize my vector bundle on open sets and I pick bases. And then the change of basis functions are, are valued in GLN, but if I pick a metric, they're valued in O. And the metric is the space of metrics is contractible. So for the homotopy theory stuff that we're doing today, you can forget about it. And then, but if you wrote down what's the data defining a principal ON bundle, again, the transition functions are valued in ON. It'll be the same composition. So these things are the same thing. So this means that BON classifies rank n vector bundles. And we've stabilized, so BO classifies, let's see, virtual, stable vector bundles. When I say vector bundles, I always mean real vector bundles. And I'm not saying that explicitly because saying virtual real vector bundles always feels kind of weird. But okay, so what is actually going on? So stable means that I don't really care about the difference between V and V plus a trivial sum. Oh, and sorry, there's one last caveat, which is that these are of rank 0. So rank 0 vector bundles are usually pretty dumb, right? They're the 0 bundle, but we're allowing virtual bundles, which are things of the form V minus W. So sort of formal difference. So let me try and motivate this for you.
Sorry.
So what?
What you call O is the colimit, is this a topological group?
It is.
Okay.
Yeah. So in some sense, it's like, when you specify an infinite dimensional vector space, you have to specify a topology, right? But you could imagine the union of all Rn of just like sequences of finite length, that has a topology. And that's the topology we're putting on this. So if you want something that's like a Hilbert space or like a Hilbert group, well, I have bad news for you. Are there more questions? Okay, so when I say formal differences, I don't want to get too into the weeds here, but imagine, so the integers. How do we get the integers? We started with the natural numbers, and then we said, okay, -3 is what we get when we take 5 minus 8. But it's the same thing as if we took 4 minus 7. And so you could build the integers set theoretically as pairs of natural numbers, where you say, okay, 5 comma 8, and that means 5 minus 8, which is -3. And then you identify, 5 plus 1 and 8 minus 8 plus 1. So you're sort of pretending that you can take differences of vector bundles, and in the same way that you pretend to take differences of integers. Well, sorry, you actually take differences of natural numbers to get integers. So the
Sorry.
Yeah.
Did you do exactly the same when you define the inverse under the
over here?
Yes.
Great question. So the inverse already exists. Like you don't need to do any completion.
Okay.
So here's M disjoint union M going into the empty set, which is the unit. So this says that M is its own inverse.
Okay, so you didn't do the same as natural versus integer.
No, so you get this for free. Whereas over here we did some sort of completion.
I see.
Yeah, great question. More questions?
So the point of this construction is to have vector bundles of negative rank to make sense of that.
Yeah, I'd say that's one way of doing it. And as for why I would want to, yeah, okay. I think that's the best answer to your question is yes. Do people have more questions? Okay, so let's pick a space B and a map to BO, which I'm going to call psi. So this data is a structure you could put on vector bundles. In the following sense. So let's say I have a vector bundle on M. So, oops, let me write this a little more clearly. So V minus a trivial bundle of the same dimension as V to make it rank 0. So if I have a vector bundle on M, that's the same thing as a map to BO. Where if I add a trivial sum n to V, that doesn't change anything. And now a B structure, or I should say a psi structure, on V is a lift of this classifying map. To B. So I have this map, and I find a map to B such that this composition is equal to this map. So this need not exist, and it need not be unique. But if you make that choice, that's a psi structure. So this is like, there's different ways to specify this, and this is one of the least geometric. So to all of you, I apologize. But what is actually going on here? So the key example, is this far enough to the right?
Yes.
Okay, great. Let's say that I did this whole construction of like, including the orthogonal groups inside each other, but the special orthogonal groups. So now I have a classifying map, and I've lifted it up to BS. So if you unwind all of the stuff over there, what you learn is that this is saying that my transition functions in my vector bundle are valued in SON for some n rather than ON. And so this is saying that the transition functions, so transition functions in SON, which implies that the vector bundle is oriented. Not just orientable, oriented. I've chosen an orientation by choosing how my transition function flows. Or alternatively, I've said which change of bases or which bases are oriented and which ones have the opposite orientation. So there's a space of lifts here, and an orientation is a connected component of that space. So you can do similar things with like spin structures, variants. You could do BO across a space X. And now this lift is just a map to the space X because we know how to map to BO. So you can encode a map to X as one of these psi structures. If you let X be the classifying space for a group G, you can encode a principal G bundle. This is very flexible. And so one thing which I guess I should mention is if, say G is a 2 group. So 2 group symmetries have appeared a lot in the physics literature in the last several years. And one of the nice things about this homotopological viewpoint, it's kind of, I don't know, cold and abstract, like from the perspective of how we usually think about physics, it's kind of like abstract and hard, but it deals with a lot of the stuff on the same foot. So 2 groups, and in fact n groups, have classifying spaces. And it's, if you set the theory up right, it's the same. Like there's no additional effort to define this, depending on how you do it. And so you could say, well, yo cross BG of your 2 group. And so a lift here is a principal bundle for G. So if you then choose a connection, then you get your gauge field for your two group. So again, I'm not going to go into the details. By this, I want to point out that this formalism of psi structures on manifolds captures like pretty much everything you might want as long as it's topological. So for example, we haven't accounted for Riemannian metrics or connections or whatever. But some of the fancy new stuff we do, like two groups, does work. Question, we're going to get back to Abortionism soon, but first, does anyone have any questions? Yes.
Do you recall what you meant by two group?
Yes, okay. So I guess the succinct way to say it is that you have a so are you familiar with like P-form symmetries? So okay, so with an ordinary symmetry, you have these codimension 1 operators in a field theory, right? But you can also make them higher codimension. So a two group says that you have an ordinary, a 0-form symmetry and a 1-form symmetry. So codimension 1 and codimension 2 operators, and they interact in a certain way. And so which you can interpret as saying that these symmetries together are anomalous, or you could package that up and say, well, really, they fit together into this more categorical structure. I wasn't prepared to talk a whole lot about two groups today, but does that hopefully give some intuition as to what's, yeah. I also think about them very differently than the physicists, so I recognize that what I say may or may not be useful. I don't know.
Is this related with groupoids or something like that?
It is. Well, okay. So a groupoid already has this sort of composition structure where you can partially compose errors, right? But what if I also put a composition structure on objects? Like I could tensor product two objects in my groupoid together. Then you get a two. Yeah, great. Mm-hmm. Cool. Who has more questions?
BG for the two group is still a space.
Yeah.
Define that to homotopy or something.
Yes. Yeah, exactly. But then there's a particularly nice model for it. Yeah, great. More questions? Okay. So what can we do with these psi structures? So what we're going to do is you choose a psi structure which encapsulates all the different fields in your theory. So for example, if your field is an orientation, then your psi structure is BSO. But if you have an orientation and like a principal G bundle, then you take BSO cross BG. And so we're going to consider Abortionism for whatever notion, whatever structure we need that that encodes all the fields in the theory. And you're thinking, okay, but I need like connections and like geometric stuff. And Abortionism is an inherently topological thing, so we're going to throw the geometric data out for now. And maybe it's part of the magic that this tells us something useful about physics. So a psi structure on M induces a psi structure on the boundary. Well, actually, it induces two. So here's the boundary. Here's the bulk. So we know that the normal bundle is trivial with two trivializations. There's sort of, you can use the outward normal vector field, or you can use the inward one. So if you pick one, then you get that, so the normal bundle, you picked an isomorphism with the trivial bundle, and you get that the tangent bundle to the boundary is the, sorry. So there's the tangent normal exact sequence, which I'm going to split by, say, choosing a connection. Tangent bundle plus normal bundle, tangent bundle of boundary plus normal bundle is the tangent bundle of the bulk. So I could re-say that as saying it's the tangent bundle minus the normal bundle, right? Since we're in the land of virtual vector bundles. And therefore, a trivialization of the normal bundle says that as stable vector bundles, these things are the same. So given a trivialization of the normal bundle and a psi structure on Tn, we get a psi structure on the tangent bundle of the boundary. The reason being that our maps to B are mapped to BO. It'll be something like the boundary includes into M, and the map for the tangent bundle factors through. So we have two trivializations. And I'm going to call this one boundary of M, and this one minus boundary. Because for psi structures, it will map. Right? Like these induce, if you think about orientations, these will induce opposite orientations on the boundary, and that matters for the definition of ordinals. Are there any questions? So, Abortionism of manifolds M and N with psi structure is a manifold X, which we come back. And let's see. Partition of delta X, or sorry, boundary X is the incoming, outgoing boundary. And then identifications of psi manifolds. Incoming X is identified with M. The incoming boundary and the outgoing boundary is identified with minus M. So keep that minus sign. So the reason is that if we look at the cylinder, and we put orientations, this is N, and this one is minus N. Because, okay, we took the same normal vector field, but on one side it's incoming, on the other side it's outgoing. So this is just a new wrinkle that doesn't change very much, but I did want to just make it clear. And so now we can play the same game with the equivalence relation, and we get out abelian groups omega n, denoted, omega n psi of n manifolds with psi structure up to Abortionism. So the inverse, like your question, the inverse of n is minus n. So it is not always true that we'll get a graded ring, but it is sometimes true. Questions here?
But the classes in BO are the same, no? For these two situations.
Yes. Yeah. So in BO, this difference doesn't matter. Or sorry, in unoriented Abortionism, but in other things it does.
So when you are inducing a psi structure on the boundary, you are making use of the tangent bundle, right? But
yeah,
that construction over there is much more general, like it's for arbitrary vector bundles.
Yes.
So
right. So I can define this on arbitrary vector bundles, but for Abortionism, I care about the tangent bundle specifically.
Okay.
Yeah.
Okay. So
wait, did that answer your question?
Mm-hmm.
Okay, cool. Who has more questions? Okay. I prepared more than I'm going to have time to say, but so probably what's going to happen is I'll talk about invertible field theory in the next lecture, which is fine. But let me see. So there are some things you can do like sort of elementary. So what did I have? So first of all, the first Abortionism group is 0 because all one manifolds are disjoint unions of S1, and S1 bounds D2. Second oriented Abortionism is 0 because every surface is a multipole donut if it's a closed connected oriented surface. And you can sort of fill this in, right? Imagine that you have your multipole donut actually in front of you, and then you make it an actual donut with with dough in the middle. But the fourth oriented Abortionism group is non-zero. And so the reason is, let's say CP2 is the boundary of some compact phi manifold. So let's choose the Fubini-Studi metric here. Any metric should work, but I like this one. And this extends to a metric on the bulk. And so in particular, so the trace of F wedge F, where F is the curvature, is closed, so I can integrate that on CP2. And what we get has something to do with, with a Chern class, and in particular, it's non-zero. But Stokes' theorem says that this is the integral on the bulk of D of this closed form, which is, so crucial here is, what is the integral of this curvature form? And I skipped that, but it is non-zero. And so this is a quick way to show that CP2 is non-zero in this Abortionism. In fact, this group is isomorphic to Z and CP2 generates. So with a little more work, you can produce other geometric arguments in low dimensions, but essentially, all progress on Abortionism has been homotopical. So this is one of these mixed lessons. On the one hand, these kinds of geometric arguments are like fun, they're interesting. Each one has a new flavor. On the other hand, homotopical means we have the standard tools of modern homotopy here. We have spectral sequences, we have stable homotopy theory and everything there. And this just makes things a little nicer. So I think that's, well, okay, I like it because that's what I do. And hopefully you will like it too.
Sorry.
Yes.
But if you take omega 2 with O instead, that's non-zero.
Correct. That's Z-mod 2.
For the
RP2
same
generates.
reason that you explained.
What?
For the same reason like you explained, I guess trace of F would be different from this.
Wait, omega 2 O?
Oh, yes.
Well, so that's going to be different. Like you can't fill in RP2.
I'm asking if it is zero or not.
It's not zero.
Yeah. The argument would be similar to that.
Well, you have to show that RP2 does not bound, and that's it's similar to this.
Yeah.
Oh, I'm sorry. Yes, it's similar to this.
Trace of F would be non-zero.
Yeah.
But can you define integrals on a non-orientable?
Ah, shoot. Okay. So when I say it's similar to this, the trick is the integral takes place in mod 2 cohomology.
Okay.
Wait, so this really corresponds to some Durand cohomology class. You can integrate it. And so for RP2, it won't look like the integral of a differential form, but it'll be the integral of a characteristic class called the second Stiefel-Whitney class. And that is your signal. There's an analog of Stokes' theorem, and that's your signal that RP2 does not bound. There's another more elementary argument that, using intersection theory that I don't remember.
But instead, if I take any Riemann surface, this will always be, you can always convert O into SO, I guess. No?
Yeah. So that says that there's sort of a forgetful map from oriented Abortionism to unoriented Abortionism. And so these things bound as oriented manifolds, so I can just forget the orientation and go back to unoriented. Yeah, so Riemann surfaces are not very interesting for oriented Abortionism. Or unoriented.
When you say that the Abortionism group in 4 dimensions over SO is generated by this, you mean that if I say that, okay, I have a connected manifold which is not the boundary of something, then it has to be CP2?
No, so almost. So if I have M, let's say that the class of some four manifold is equal to K, then M is boarded to K copies of CP2. So when K is positive, it's clear what this means. When K is negative, we need to take minus CP2. So this is kind of,
with opposite orientation.
What?
CP2 opposite orientation.
Precisely, yeah. So this is more conventionally denoted CP2 bar, the opposite. Great, more questions?
So I'm a bit confused in your definition of the Abortionism group. You only use the tangent bundle, or?
Yeah. So you use the manifold, so you use the tangent bundle to put the psi structure on, right? So something like an orientation or a spin structure is just a fact about the tangent bundle. And so you use that to define the psi structure, and then you use the manifold to get, for example, this, to write down the equivalence relation. And then that gives you the Bordism group, or the Bordism groups. What's up?
This argument, what happens if you try to apply the argument you give for CP2 to CP1? I mean, CP1, you also have Fourier symmetric, you also have closed form.
Good.
So you don't know that it extends. So how do you know here it extends?
So the trick is, you want to take the let's see. So the curvature form.
I mean, in dimension less than 4, doesn't, I mean, it vanishes automatically.
Right. So I mean, of course, it bounds the 3 strip, but what he's sorry, the 3 ball. But what he's asking is where in this argument does it fit?
I mean, this automatically is 0, right? Like, F
Yeah, but why? So if you just take the
dimension-
trace of the curvature. So I know you can do this if you're willing to use the complex structure. I think the trick is.
I mean, but this argument can only work like at least in like 4 dimensions, right? Because you have a 4 form.
Right.
And in any dimension less than 4, like it's going to automatically vanish.
Right, but you could have just taken F instead of the trace
Yeah,
of
you
F.
can take a 2 form. Why?
Yeah. So the answer is that so in order for this to give you something which so I sort of waved my hands and I said, oh, this extends and therefore the curvature extends and therefore the thing extends. What you really need is you need a polynomial valued on the Lie algebra SON, which is invariant by the group acting by the adjoint action. And so that somewhere along the way, Chern-Bay theory turns that into this canonical closed form. And so if you ask, well, what are the invariant polynomials on that Lie algebra? There's just in dimension 2, there's only the identity. Or sorry, there's only the 0 polynomial. And so if you say, okay, well, I have U1 instead of SO2, then you do get something. You get then just F, F is invariant in that. But then you're asking for the much stronger condition of not only do I bound, but do I bound as an almost complex, stably almost complex manifold. So the tangent bundle isn't just oriented, it's stably isomorphic to a complex vector. And so when you put that in, then CP1 does not bound. But as just an oriented manifold, this thing isn't, like F just isn't invariant. Yeah, great question. More questions? Okay. So I'm running a little low on time, so what I'm going to try and do is talk about the let's see. Maybe I'll do that next time. I don't know. Okay, so I think the right thing to do here is I'm going to skip a bunch of details, tell you a little bit, like just a few of the highlights, and then I'll figure out what to go into tomorrow, in the next talk after that. But I want to mention, because we've been sort of doing a bunch of math, I want to mention where this is going to begin to connect to physics. So the first thing I want to mention is that associated to this data, the different kind of Bordism we can do, there is a space, called the Tom space. Bordism groups. They're defined to be homotopy groups of this Tom space. So the construction is like actually like fairly geometric and relatively down to earth. And the proof is, a little less down to earth, but honestly not that bad. And so this is how calculations go. So in fact, if you've heard of spectra in the world of generalized cohomology, I currently don't have the time to talk about that. Like, starting now, we run over time and that would be bad. But you can really, so there's some like stability issues here where it's like, okay, you have to make some choices here and then the dimension here varies. But if you're willing to work with the Tom spectrum instead of the Tom space, all of that just drops out and things simplify a little bit at the cost of having to, add more formulas. And so this is how this stuff usually goes, is there's going to be a Tom spectrum. MT psi. So yeah, so maybe I'll say more about that next time. And so but what I'm going to do the last few minutes is talk about invertible field theories. What's up?
That does stand for the n homotopy group of that space.
Oh, I'm so sorry. Yes, this means the big N homotopy group.
And is that n the same as the little n?
No,
And so what is the relation between both?
it depends on stuff I didn't tell you here. So like, this is the annoying thing about using the space rather than the spectrum is that it depends on some auxiliary data. And so, you know, if you pick different auxiliary data, everything's compatible. But this would take more time to say than the 3 minutes I have left. Yeah. So I recognize I'm going a little too fast here, but if I'm always happy to talk about this stuff later. So if people have questions, I'm happy to chat about it. And I'm going to figure out what parts of this I can talk about tomorrow as well. More questions while we're stopped. So I'm definitely going to say more about this tomorrow, but yeah, okay, there's not enough to treat this really precisely, but you can upgrade into a category for psi. So the objects are closed n-1 dimensional psi manifolds. The morphisms are n-dimensional orders. So now, instead of just saying, oh, this says that these two things are equivalent, this is a morphism, so sort of a function from M to N. And then composition is glue. So this is a category, and there's fancier variants of that I'm not going to worry about that show up if you want to encode things like locality. But a topological field theory is a functor from this Abortionism category to vector spaces, complex vector spaces, such that disjoint unions are mapped to tensor products. So if you want to be really precise about like, what did I mean here by this isomorphism, there's a bunch of category theory stuff that we're not going to talk about right now. But the idea, so this is this idea due to Atiyah and Siegel. And I'm severely out of time, so I sadly can't like motivate this. But one way to think about this is I want to compute the partition function of something. Well, I can do that. I should be able to do that by chopping it into pieces, computing something on all of those pieces, and then putting that data back together. And that's what this Abortionism thing is doing, is it's saying, okay, that's really composing a bunch of maps, these like time evolution maps, to obtain the partition function out of it. So it's the hour, so I'm going to finish with the next sentence, which is, so the classification of TFTs is complicated. But invertible TFTs so invertible TFTs are I'll give the definition next time, but they're almost but not quite trivial. So they're an interesting special class, and they show up in applications. So invertible TFTs can be classified by their partition functions. Oh, and I need to add one more word, which is invertible unitary. They're classified by their partition functions, which are Abortionism invariants. This idea is due to, or sorry, as a theorem, this is due to Fried-Hopkins. in their long 2016 paper. And so the idea is if you want to know what the invertible field theories are for some physics reasons, such as anomalies or studying SPT phases, you can calculate what all the options are by computing a Abortionism group and seeing what the possible Abortionism invariants are. And then there's your answer. So the stuff that's going to happen in the next 2 lectures, a lot of it is going to appear because of this fact. So I'm really sorry for going over time. Thank you all for listening, and please let me know if you have more questions.
By invertible, do you mean that the vector space has dimension 1?
Yes. So the definition, like, it's not just that; it's also I want all morphisms. So the value assigned to every Abortionism also has to be invertible.
It means that the functor you defined is an isomorphism. Or...
So here's a good analogy. So this feels like a complex value function on some sort of space, right? Like a function from just some space X to the complex numbers. So when I say invertible, I want there to be 1 over F. So it's not invertible like I can go backwards. It's invertible in the sense of like multiplication. So what does that mean? That means this avoids 0, and then I can divide by that. And so here we're saying this avoids the non-invertible objects of this, the non-invertible morphisms. So there's some other thing Z prime, such that Z tensor Z prime is equivalent to the trivial field. So in physics, you can think about this as some quantum field theory, which is not, it's almost trivial. All of its state spaces are one-dimensional, but it's not actually trivial. And so there's some other thing you can stack it with. You can put both of them on the same medium with minimal interactions, such that when you do that, you get the trivial field, like no physics whatsoever. But yeah, so the precise definition is Z factors through the invertible things in this category under tensor products, which, like you said, is one-dimensional. Yeah.
When you said partition function, you really mean partition function for the physics definition, like path integral or.
Okay, I should have said this. So let's say that I have a closed N manifold. That's a Abortionism from the empty set to itself. And so this condition forces Z of the empty set to be C. So I get a linear map from the complex numbers to the complex numbers. And so that's some number. And this number is called the partition function. Now, that is a completely weird definition of the partition function compared to what it should actually be in physics. And so the idea is, if your topological field theory is described by a path interval, say like Chern-Simons, this should be the same thing as that. You know, we don't know how to make path intervals precise, really, but as far as we can tell, it's giving the right idea. But yeah, I'm glad you asked about that.
Is this cobordism category a 2 category naturally or not?
So the way I wrote it, it's just a 1 category, but you can modify it into higher categories.
And can this topological field theory be adapted to that or enhanced?
Yes. So quantum field theories are supposed to be fully local, right? And so the way to implement that is to say, well, why should I stop cutting in one direction? I should also start cutting in like other directions. And then you end up getting, this higher categorical structure coming out of that idea. And so then you replace this with an N category, that with an N category, and it's, things get very complicated, but they work. And that is how a lot of people in math think about topological field theories. It gives you the right ones from a physics point of view. Yeah.
In the derivation, if I use the tone spectrum instead of the tone space, the 2 N becomes the same on the
Yes.
right? Okay.
Yeah. Ooh, I should have said that.
Maybe repeat the question.
So what he asked is, let's say that we use the Tom spectrum instead of the Tom space. So the advantage is you don't have to worry about the stability issue, but the disadvantage is you have to think about spectrum, which is not as common it's not as commonly taught in physics literature. So then big N and little n are the same. Yeah. So that does make things a little nicer. Great. More questions?
So the Kali structure is going to have a physical meaning eventually?
Yes. Okay. So let's say that you're working on a physics problem. Like, let's say that you want to know the whether heterotic string theory with E8 cross E8 has an anomaly. So then you have a where's a good place to erase? How about here.
In the middle, in the middle.
Oh, okay.
That's great.
So the E8 cross E8 heterotic string. So what's the data here? So there's two E8 bundles. So there's a spin structure, two E8 bundles. So if I use this side structure, that says that M has a spin structure and two principal E8 bundles. And so I would want to study this notion of cobordism to study anomaly cancellation in the heterotic string. And if you're thinking there's a Bianchi identity that says it's not really this, you can take care of that too. And so you would just take, you would lift slightly more to whatever the structure is. So there's a condition on the characteristic classes that says that the P1/2 of the spin structure is the same as the sum of the characteristic classes for these. And so you would lift to a space that enforces that condition. So that's the sense in which the psi structure represents the invisible. You ask what data do I have in the field theory that I care about, and you just encode that thing. Did that help answer your question? Great. Who has more questions?
Okay, let me just so the connection of invertible field theory TFTs with string theory is the interpretation that of like string theory on a rigid Calabi-Yau threefold, like topological string theory on like the B model topological string theory on a rigid Calabi-Yau threefold, so that doesn't have any complex structure deformations.
The B model is usually not invertible, right?
Usually, but if there are no complex structure deformations, then you only have the holomorphic volume form, which is the Hilbert space is basically just one-dimensional.
And that would do it. So the best answer to the question I can give right now is I don't know. Can we talk about it later? Because that's an interesting question. But the way in which I know invertible field theories typically enter string theory is through anomalies. Like you want to understand like an anomaly cancellation question like this one. Well, that turns into, is this particular invertible field theory true? But that doesn't mean that's the only way in which it can enter. Yeah, I'm curious about this one. Great.
So maybe someone online has some questions because we have some online participants. I don't know if
There's no question in the chat.
okay. So maybe it's a good time to take our
Yeah, sounds good. Thanks all. Okay.